this assessment, we're going to use bond dissociation energies to help us pick between these two radicals and identify which is most stable. By keeping both of them as CH bonds and imagining hypothetical reactions of these CH bonds becoming the respective radicals, we can figure out how much energy we have to put in to form each. And the amount of energy we put in to form each is going to reflect the stability. And so what we notice about this CH bond is in addition to being a primary CH bond, it's also next door to a double bond. And so technically it's an allylic CH. And so the number we're going to use for that bond is 87, shown over here. So 87 kilocalories need to be put in to form this radical. Over here, we have a tertiary CH bond. In order to form the tertiary radical up here, we would have to put in 91 kilocalories per mole. If we have to put in more energy to form this radical, that implies that this radical here, the allylic radical, is the one that is most stable. Why is it most stable? Because that radical can be stabilized by resonance. And so we can imagine a resonance structure where we show that radical delocalized onto another carbon. By delocalizing the radical, we make it more stable. How much more stable? 4 kilocalories per mole, more stable than the tertiary radical that is stabilized by hyperconjugation alone.